before we move on, I would like to share the PV CD-ROM website. And I would like to show you a few things before we continue. PV CD-ROM, okay? Can you see the website on the screen now? All right, good. So, if you want to learn about solar cells, in this website, so it's for solar cells to begin with, right? So if you want to know about solar cell operation, you go to chapter 4 for solar cell operation here, and then the whole list down here. So the whole sub chapters down there are for solar cells, right? Solar cell operation, solar cell parameters, resistive effects. You can even learn about design of solar cells and even manufacturing of solar cells. So if you want to go for your internship or job interview later on, if you want to go for any solar companies, for example, like Jinko, JA, First Solar, QCells, Longi, SunPower, for example, this is one of the places that you might want to check out, right? For the fundamentals of the solar cell. So yesterday we talked about carrier generation and operation of solar cell briefly. So let me just show you an animation to illustrate so that you get to understand the mechanisms, right? So this is basically a structure of a solar cell. So it is a p-n junction. So in this case, you can see that P side is thicker. So that means the wafer is p-type, and then the n-type here is the emitter, the diffuse emitter, the thin layer on top of the wafer. So just to show the difference, okay? So p-n junction, and then you have front contacts on the front side, and then rear contact on the rear side. So let's look at what's actually happening in the solar cell upon the light incidence, okay, or the photon incidence. Start photons. Photon is incident, okay? Let's say it's just a photon, a single photon. So if the photon has an energy of more than or equal to the band gap, so if you're talking about silicon, then the photon has to have energy of more than or equal to 0.12 electron volt. Light will be absorbed, okay? We learned about this in generation. On the other hand, if the photon energy is less than the band gap, the photon will be passing through the silicon without being absorbed, okay? And then it will just leak through the back, okay? Leak through the back of the solar cell, unabsorbed, okay? So in this case, since the EPH is more than or equal to, so the light will be absorbed. As a result, the absorption of the photon creates electron hole pair, okay? So remember the 4 steps: light absorption, carrier generation, carrier separation, and carrier collection, right? 4 steps in solar cell operation. So now we are at step number 2, generation of electron hole pair. And then see next, okay, let's see. Okay, now the red one is the electron and the blue one is the hole, okay? Now I want you to look at this, the what I call the space, the location where the electron hole pair is generated. Coba tengok sekarang dalam where are they generated? Are they generated in n-type or in p-type site? Okay, for this example, they generated kat mana? In n-type or in p-type, the electron hole pairs. Look at the location of the electron hole pair now. Where are they? N-type, right? So that means the light is absorbed. In this case, this particular photon, this specific photon is absorbed in n-type, right? So this may be a UV photon, for example, because we learned that a high energy photon will be absorbed near the surface, right? So if you're talking about middle energy like green or yellow or orange, for example, then they may be absorbed somewhere in the bulk, okay, in the bulk, right in the wafer, for example. And if you talk about red photons, they'll be absorbed at the back, okay, near the contact or before the contact. So in this case, just to illustrate the UV photon, so look at the photons, the light absorption, the photon absorption results in electron hole pair generation in n-type. So now, where will the electron go? Which side will the electron go? To the front side or to the back side? Electron, the red one. Where do you think it will go? Front side or rear side? We are into our third step, carrier separation by the junction. Any guess? Okay, Rafael said rear, okay. Any more rear or front? The question is, where will the electron go? The electron is the red one. Front. Okay, so front, I got front. Mushfiq front. Nabila front. Okay, any more? Two more answers? Two more guesses? Come on. Front or rear? We're talking about carrier separation now. Step number 3 in solar cell operation. Front or rear? Last one perhaps. Faris? Front or rear? Faris? One more? Anyone? Rear. Okay, we have two rear, two front. Rear. Okay, Faris said rear. Okay. All right. Let's see. Okay. Let's see, where does the red one go? So where's it going? Front, right? So it's going to the front. Remember, the electrons will be collected into the n-type region, okay? Or on the negative side. Electron will be collected into negative side. Okay, maksudnya negative side n-type lah. So electron will be going to the front, going out through the front contact. And the blue, the hole will be collected at the back, positive side, okay? Electron will be collected in the negative side, hole will be collected in the positive side, right? So ideally, the minority carrier, in this case, a hole. Remember just now the electron hole pair was created in n-type region, okay? Let's zoom in a little bit and try to relate to the fundamental that we learned before. Ideally, the minority carrier, in this case, hole, is okay. Electron hole pair is generated in n-type. In n-type, which one is the majority carrier among this electron hole pair? In n-type, which one is the majority carrier between this electron hole pair? Electron or hole? Majority carrier. Electron, right? So in n-type, electron is the majority carrier, right? On the other hand, hole is the minority carrier, right? So in this case, at this particular point in the PN junction, since the electron hole pair is generated right in the n-type region for this particular photon, the electron doesn't have any problem to travel to the contact because it is already a majority carrier, okay? So it is an electron sitting among many more electrons as majority carriers in n-type. Therefore, the probability of recombining with a hole is very, very low. Even though n-type also has some extent of minority carriers, which are holes, right? But the probability of recombination is much lower for a majority carrier-like electron sitting in n-type neighborhood, which are filled with electrons, okay? On the other hand, at this particular point, a hole is the minority carrier sitting within n-type region, okay, where the majority carriers are electrons. So the probability of recombining is very high. So therefore, in order to be collected, the hole has to cross through the p-n junction to be a majority carrier on the p side, okay? So the challenge is really for the hole, because hole was generated in terms of electron hole pair in n-type beforehand, right? So therefore, it has to cross the p-n junction in order to be collected by the junction, in order to be swept into the p-type region and survive as a majority carrier in p-type region, okay? So the moment the hole crosses the junction and survive in p-type, crosses to p-type, now the hole becomes a majority carrier. So the moment the hole becomes majority carrier, the challenge is no longer a big deal, because it is now sitting within the p side region, where the region is filled with so many holes. So again, even though the holes are the majority carriers, we still have the minority carriers, which are electrons in this p-side region. So if that's the case, the probability of recombining is still there, but it will be very, very low, because the majority carriers in this case are the holes in the p-side, okay? So look at the holes now, is drifting to the p-side region to be collected. And then the circuit is completed, okay? So is it okay so far? Just to illustrate the crossing of the junction and the survival before the collection. Is it okay? Is it clear? Can you see now from this simple animation? Okay, what if, now the question is, I have a question. What if we are talking about, if we restart, okay, okay, let me just restart. Okay, what if this incident photon is yellow photons ataupun green photons, which will be absorbed in the middle of the wafer right here? I'm pointing on using my cursor now. Say if this electron hole pair is generated down here, so what will be the movement then? What will be the movement? Which carrier will be facing a big challenge to cross if it's generated down here? Anyone? Just move the electron hole pair a little bit down into the wafer instead of in the n-type. Okay, electron. Kenapa, Juwaria? Why is it electron then? Why is it electron, Mushfiq or Juwaria? You can unmute yourself. You can write down as well. Okay. So electron is the minority carrier, right? So electron is the minority carrier in this case, because now if you generate down here electron hole pair, so the hole has no problem to be collected at the contact at the back, because it's already sitting in the region where it is a majority carrier. So the probability of recombination is very, very low. On the other hand, the problem is really for the electron. In order for it to be collected by the junction there, okay, by the electric field at the junction and crosses to n-type. So if the point of generation is really here, then it has to cross from here to there, right? Here to there. So this is pretty much distance it has to travel in order to be collected by the junction. So this is actually the diffusion length that we were talking about last time in the class. So if the diffusion length, if the diffusion length here is long enough to be able to reach the junction, okay, if the diffusion length of the electron is longer than the distance between the point of generation and the junction, then the electron will be collected. Okay, then the collection probability will be 1 if like, right? On the other hand, if the diffusion length of this electron generated here is less than the distance from the point of generation, which is here to there, then the electron will not be collected. So that's what we discussed last time. So I think this is just a very simple animation, but it explains a lot. Okay, it helps us to relate with what we learned before. Right, done. So on this page also, you can come and check it out here. Okay, let me just finish a few more minutes before we move on the slide. You can also play with, okay, we've gone through this. Okay, this is the EQE we discussed yesterday. Let me just zoom out a little bit to show you, okay? So EQE here is the green curve, okay? The total curve here is the EQE. Zoom in a bit, okay? EQE is the green curve. So this green curve is a result of summation of this blue curve, EQE of the emitter in the solar cell, say your N-type is now your thin layer, plus with EQE of your base, the collection in the wafer, right? So it's the summation of the EQE of the two regions, N-type if you like, the blue one, and P-type for the red one, okay? So N-type is the emitter on the surface, and then red one is the base or the wafer, okay? So adding blue to red will give you green. So let's just try to play with this and see what if, look at the whole total and the components here, blue and red. What if your diffusion length is very, very low? Now it's sitting at 10 micron, okay, which is way longer than is required because the typical thickness of the emitter is somewhere about 200, 300 nanometer. So if I just slide this to the left, to the lower value, look at the whole change there. So as a result of going to the left, so lower diffusion length of the emitter, the blue collection, the blue curve is now lower than it was, right? So that means the emitter diffusion length is affecting the emitter collection probability or the QE of the emitter. As a result, since the green one is the addition of blue and red, you're going to see reduction in the short wavelength region as well. So I explained this one yesterday that the front surface of a solar cell reflects or is reflected in the short wavelength region between 300 to 500 more or less. And then what's happening in the bulk is reflected between 500 to about 900, if you like, in the central region, because you can see the base collection is there. And then what happens at the back of solar cell is reflected above 900 nanometer. Okay, so that's the effect of the emitter diffusion length. So let's see the diffusion length is like that. For example, let's look at the second one. What if your emitter surface recombination velocity, the SRV, we discussed last time a couple of times, if the SRV is too high, see the QE of your emitter will be dropping. As a result, the total QE will also drop. Okay, and we don't want to have high SRV. We want to have low SRV, as we discussed last time. If your SRV is very low, then the QE will be going high and it's limited by the emitter diffusion length. So the same goes to the base. If you simulate the base here, if you say now the base diffusion length is about 100 micron, if you slide it to the right to show that the diffusion length of the carrier in the base is longer than 100 micron, let's go to longer than 100 micron, you won't see any change in the emitter, but you'll see the change in the base because it's only related to the base. So the rate is really going higher, and as a result, your total QE is also higher due to the contribution of the rate curve. On the other hand, if you move to the left, where the base is having poor quality, therefore the diffusion length is lower, so the rate curve reduces. As a result, the rate curve reduces as well, right? You can also play with the SR base recombination velocity there. You can also see the effect. If you have higher recombination velocity in the base, then the QE is going lower to the red and to the green. Okay, so this is the thing that we discussed yesterday. Let me see what else I need to show before I move on. So you can always come here and try for yourself in order to understand more, right? I won't be able to show everything though because it's just too many things here. When I was doing my PhD, this whole website is used as one course. Okay, so the course is called Solar Cell. I still have the book here. I can show you one of the courses I had to take during my PhD. You can see this book. The camera is you can't see that. This is the book. Okay, Solar Cell. This whole book is converted into this ebook. Okay, this website. So yeah. Okay, this is by Professor Martin Green of UNSW. So it's like a course, a single course So I can't afford to go through every single thing because it's just a small chapter within our course. So let's just go through yourself later on. Okay. So many things if you want to learn from here. Okay, let me just unshare and continue with our slides. So is it okay? Can you see the QE correlation? What's happening if you change what? Can you see it now clearly than yesterday? Is it clearer now? Okay, yeah. Not okay. Okay, right. Tak okay kena cakap tak okay I need to know whether you're okay or not. Right, let's move on with our slides. All right, can you see the slides now? Okay, good, right. So we talked about a couple of things on solar cells yesterday, and today I'm going to continue with this slide. So if you look at the annual PV production by technologies, more than 90% is dominated by crystalline silicon-based technologies, which is the first gen, right? Made up of monocrystalline and multicrystalline. In fact, now it's more than 90%, and only a small chunk belongs to thin film solar cells like amorphous silicon, CIGS, cadmium telluride. Okay. So if you want to break down, for example, if you want to see this 90% contribution, this by, you can see this 2018 data. So you can see in 2018, the one on the right here, far right. So from here to there, to up here, it's all silicon-based technologies. Okay, so all silicon-based. Only the top here, I think about less than 10% or so is what is on thin film. Well, the rest of the 90% plus is on N-type mono silicon, P-type advanced mono, P-type advanced standard mono, multi advanced and standard. So it's more than 90% in the market. So if you look at 2018 data, out of the 90% domination, so both are equally represented, mono and multi. But during this time, the mono is not what you call the mono solar cells costs have not dropped enough. Okay, but now if you look at the latest projection and the latest consumption or latest production, mono is now exceeding multi. So well, I talked to you last time about this. Crystalline silicon is a poor light absorber, right? So it has a high reflection level, which is about 40%, and it is also an indirect bandgap semiconductor. So it has a poor light absorption. So how come it is so dominant? Okay, how come it's so dominant? So why crystalline base then? Why dominant? Why so dominant? Why the first one is silicon is an abundant source in the form of silicon dioxide, earth crust, and then silicon is built. The silicon technology is built from extensive knowledge from microelectronics industries like integrated circuits that we have been championing all this while. So it's been around for what 50, 60 years, more than 60 years already in the market. And the knowledge is just extensive. You can find textbook, ebook, papers, and many things. So it's already a mature technology. So therefore, moving from integrated circuit based on silicon to solar cell based on silicon is not a big deal. In fact, if you look at the industry, the manufacturing of crystalline silicon solar cell is much simpler if you compare to the manufacturing of integrated circuit based on silicon as well. So if you can tell this by the cycle time. So if you want to complete a fabrication of IC, for example, you might need about 2.5 months to complete. So if you talk about crystalline silicon solar cell, you just need a couple of hours to complete. So that tells you how much simpler it is, right? The silicon has a near ideal band gap of 1.1 electron volt for conversion process. So the ideal conversion process for PV conversion is about 1.4, which is close to gallium arsenide. Okay, gallium arsenide 1.4, cadmium telluride 1.4, 1.5. But silicon is not that bad. Okay, not that bad. Silicon is non-toxic, even though we can argue the processes involved to fabricate the silicon solar cell is toxic in nature at some point. You can argue that. But the silicon itself is non-toxic. If you compare to gallium arsenide, which is toxic in nature, if you compare to cadmium telluride, which is also a bad one in nature, silicon is not comparable to those, right? Silicon has high efficiency, and in fact, the efficiency is increasing, even though the conversion efficiency nowadays is already approaching the theoretical limit. Okay, so we can see now the conversion efficiency of the best. I read an article yesterday from Longi, if I'm not mistaken. Longi, oh no, Jinko Solar, the one that we have in Prague. Jinko has just successfully manufactured one of its technology based on silicon with 25% mass production. Okay, 25% efficiency. So if you want to know the theoretical efficiency of the silicon solar cell is around 29 to 30%. Okay, so that is the theoretical limit defined by Shockley-Queisser limit. You can check it out later on. It's called Shockley-Queisser SQ. I just write down as SQ limit. So silicon is about 29%. So now we are already at 25%. Single junction, just a single PN junction. So we're only like 3 to 4% away from the ceiling, from the theoretical limit. So beyond that, you cannot go further. You have to break the glass. Okay, you already did. Kepala dah sampai kat ceiling. You know, so it's only like 3 to 4% away from theoretical limit. So, and it keeps increasing bit by bit. And as a result of the gradual increase in efficiency, if you can recall, US dollar per watt. So if watt decreases, so reducing technology costs. So this is the Shockley-Queisser limit that I told you. So you can check it out again. So Shockley-Queisser limit. So on the y-axis, you can see the conversion efficiency of the current solar cells that we have. And x-axis shows the band gap of the semiconductor, ranging from 0.5 or 0.7 really for germanium up to 2.3 maybe, 2.3 for cadmium sulfide. Cadmium sulfide to germanium. So germanium is the lowest, cadmium sulfide is the highest in this particular case. And gallium arsenide, look at gallium arsenide. And you can see three curves here. Before that, you can see three curves. The first one here is AM0, which is for extraterrestrial application. I talked to you about this yesterday on the satellite and stuff. Extraterrestrial satellite. For ground application, Earth application, we're talking about 1.5 Earth application. Black body limit is the theoretical limit, right? Black body calculation. So look at now let's just look at 1.5 curve. Look at this curve, 1.5. Okay, get that curve, 1.5. So with 1.5 solar spectrum, AM 1.5G, the optimum band gap is around 1.5. 1.4, sorry, 1.4, which belongs to gallium arsenide. 1.4. So look at silicon. Silicon is 1.1. Well, not too bad, not too far away from the best condition. Okay, 1.1. Silicon 1.1. Near ideal, but not the ideal one, right? Cadmium telluride is 1.5. CIGS is tunable, so it's somewhere 1.2. Indium phosphide 1.2, 1.3. So those are among the optimum band gap, right? So do you have any idea why the curve is like that? Why is it taking the dome shape? Kenapa dia bentuk macam dome? Why is it optimum in the center, but if you go to the left or if you go to the right, the conversion efficiency drops. Any idea for the solar cell? Any idea? Kenapa pergi kanan, pergi kiri dia low? Say p-type, n-type, and photons. Any idea? First one is because it is aligned to the solar spectrum. Our solar spectrum, if you look at the solar spectrum, the peak of the spectrum is somewhere around 600 nanometer. Okay, around 600 nanometer. AM 1.5 lah. Go back to the AM 1.5. See this. It's somewhere 600 nanometer, which matches with the peak of this region. Okay, so that's where the photons are. Okay, to be harvested. So the peak of the photon intensity is there. So if you go to the right, so let me just explain. So that's the best, the central condition. If you go to the right, you are increasing the band gap of the semiconductor. So what happens if you increase the band gap of the semiconductor? If you use 2 point something, for example, what happens? Is it any easier? Is it any easier for the photons to be absorbed if you compare to the lower band gap? Go back to EPH versus EG that we learned before. If you use band gap that is high, okay, you said, if Zan said no, you said no means it's going to be more difficult, right? So if you're, okay, let's revisit this equation. That's why I keep repeating EPH in comparison to EG. So remember the light absorption will only take place. So below you have the light absorption, then the generation, separation, collection will follow. But you have to have the light absorption first. So that is the very first gate that you need to have in order to ensure solar cell operation. So if your EG is high, so it's going to be more difficult for the photons to excite the valence band electrons, right? So if it's more difficult, then what's going to happen? So you're going to have, can you have the light absorbed more easily or harder? Is it easier or harder for the light to be absorbed? Easier or harder? You can write it down. Anyone? Easier or harder? High EG. The band gap is very high. The barrier is very high. Harder, right? So harder for the photon to be absorbed. As a result, you will not be able to generate so much photons. Okay. So as a result of that, you won't be able to generate so much electron hole pairs. As a result, you will end up with low current. Low current from the solar cell. But if you go to the higher side, the voltage of that can be generated by the solar cell can be high, because the voltage, the VOC, okay, let's relate back to the curve we learned yesterday, the IV curve of a solar cell. So here is the current, right? The JSC and the VOC. JSC, VOC, the interceptions. If you go to the right, your current will be low, your short circuit current will be low, but the voltage will be high, because the voltage is proportional to the band gap. Okay. On the other hand, if you go to the left, so let's just go to the left. Let's relate with EPH versus EG again. So now the band gap is very low. So if the band gap is very low, is it easier for the photon to be absorbed? Now the barrier becomes smaller, smaller, smaller. Easier, right? So as a result, more photons will be absorbed. Okay, more photons will be absorbed. And this will result in high current. High current. But Remember, the VOC is proportional to the band gap, right? So you will end up with low VOC. So going to the left means you're going to get high current, low VOC. Going to the right means you're going to get low VOC, high VOC, but low current. So it's a trade-off. If you go to the left, so you're gonna get low VOC, high current. If you go to the right, you're gonna get high VOC but low current. So the problem, both sides have its own challenges. Okay, so the best one is in the center where you have high current and decent VOC, I would say, right? High current and decent VOC. So that will give you the optimal conversion efficiency of the solar cell. So that's how you can explain this graph. So this is just a world record chart compiled by NREL, National Renewable Energy Lab in Colorado, Golden, in the US. So you can see the world record. For every single world record, there will be a new point on the chart. Okay, so if you look at this chart, if you look at this point, for example, EPFL back in 1991, 92. So this represents a single world record, for example. Okay. So if you look at crystalline silicon solar cells, so the legend is in the blue color. So you can divide to many different technologies there. The one with concentrator, the one without concentrator, multicrystalline, heterojunction, intrinsic by Panasonic that we saw yesterday, and also thin film crystal. So for example, if you want to see the non-concentrator technology, that means the solar cells which are not placed under a big lens. Okay, solar cell you can also place on a big lens so that you can concentrate the light. Okay, when you were small last time, pernah main guna kanta tak? Have you ever played with magnification lens to burn, burn the dry leaf or something? Pernah main dengan kanta kecil tu? Pernah kan? So you concentrated the light, right? Concentrated light and you saw something burning. Betul. Pernah buat your own experiment backyard kat rumah kan? So you can concentrate the light and then burn something down there, right? Daun ke whatever lah. So you can burn something down there. So kalau you pakai daun kering, then you can burn the dry leaves, right? So the very same principle applies here. You can use a big lens in order to concentrate the incoming light to the solar cell, or you can also use micro lens, the very small micro size, place on the cell dalam panel. You can place micro lenses and concentrate the light at all the locations. You can even use nano lens to do the very same thing. So that particular case is called concentrator technology, where you concentrate the incident light. If you're talking about solar cells or panels which don't use any lenses, so then we are referring to the non-concentrator technology, like the blue one here. Okay, so let's look at the trajectory of this line. Okay, back in 1976, so 12%, 14%, more or less. Look at this. The record is held by UNSW multiple times until, so back in 2000, it goes up, Panasonic, sampai ke sini ya. So the latest record here was announced back in 2017, I think, 2017 or 18 there, around 26.7%. Okay, so that's only one example of the technology that we're talking about. So you can also look into other technologies. If you stack the solar cell with multiple junctions, PN on PN on PN on PN on PN, so you will end up with multi-junction technology. So that will even give you higher efficiency, but they are at higher cost. Okay, for example, if you look at this NREL 6 junction, 6J here means 6 junction. PN on PN on PN on PN on PN on PN, 6 stacks. PN satu cell, PN second cell, PN third cell, fourth, fifth, sixth cell. So altogether, that will give you about 47.1%. At 143 times X here means 143 times concentration of the sunlight. So it's not one sun, it's 143 suns. Okay, then that will give you 47.1%. You can even have a look at this perovskite, for example. Perovskite, Where is perovskite? So let's look at this. Started somewhere there, the world record by EPFL back in 2012. So that was just about 14% or so. And now it's gone up to around 25%. 25%. That's for single junction perovskite. And we also have a tandem perovskite on silicon. Okay, tandem perovskite on silicon. You can see somewhere 29.1% by Helmholtz-Zentrum in Berlin. Okay, so 29. If you stack perovskite PN on silicon PN as two cell, top cell and bottom cell, you can get up to 29%. So the rest you can check it out for yourself. Gallium arsenide, CIGS, cat telluride. You can in fact refer to this for your presentation next week. Okay, if it's related to your device. So this is basically if say this year one institution or one company broke the record or declared another world record, 1 point will be plotted on this chart as a new world record claimed by certain institution. And for each world record, it has to be verified by an independent institution. For example, if katalah USM buat satu world record, we cannot just claim that we have just came out with a new record. It has to be independently verified by an institute appointed by PV society, like Japan or German or US or China. Ada a couple of institutions in the world which are given certifications to verify the world record cells. Okay. So how did the silicon get so cheap? Let's go on for another 5 minutes or so. So how did the silicon get so cheap? So this is Professor Martin Green from UNSW. So he's also dubbed as father of photovoltaics. He's the one who really pushed the development of solar cell since 1960s or so. Okay. So if you look at this curve, this is a curve called PV learning curve. So it shows you the technology cost or the sales price of the PV modules back in 40, 50 years ago, right? I'm going to show you later on. But this one is the y-axis in terms of USD per watt, and the x-axis is in terms of cumulative PV module shipment based on the shipping or the production by companies. And in 2019, the cost has dropped to around 24 cents per watt. Okay, 24 cents per watt due to economies of scale. Economies of scale means what? Means you have more and more companies manufacturing the same technology and provide the panels to the market. As a result, you end up with high volume of the panels in the market. So that's called economies of scale. So now it's gone down to 24 cents per watt. So if you want to look at the very same curve as well, the dollar per watt on the y-axis, but the year on the x-axis, you can see that back in 1977, the cost for this technology is about $76 per watt. It was ridiculously expensive, right? Dollar per watt. $76 per watt is like what? Times 4, 300 RM per 1 watt. Okay. If you want to go into a toilet, for example, you need an LED bulb of what? LED with a power of perhaps 10 watt. So that's like 3,000 ringgit, Malaysia, for example. It was ridiculously expensive. And now it's gone down to 2015, it's gone down to 24 cent, 30 cent. And last 2 years, it's gone down to 24 cent. And last year, it has gone down to 20 cent, right? So it's gone down really significantly. So as of 2020, it was already 20 cent per watt. Super cheap. So this is just a breakdown of the cost. So 2018, it was still at 30 plus cent per watt. So this is, you can see the legends here. Here is the panel, the price of the panel, and if you go down here is the price of the solar cell inside the panel. So it's slightly cheaper than that. If you go down here, orange is the cost of the wafer inside, and then the cost of silicon eventually, right? Silicon. So silicon makes the wafers, wafers makes the cell, cell makes the module. Okay. So going up from your material to your panel. So then the cost add up accordingly. So the thickness of the wafer, for example, now we are at 2020. So the thickness is roughly about 165 to 175 micron in the market. So this is the thickness being used in the market by first gen solar manufacturers. So it's going down. You can see the trend. It's going down. It's going thinner and thinner into the production line later on. So if you talk about the recent technology, it is called PERC solar cell. So the previous technology was called back surface field technology. Back surface field, there, BSF. So this technology is going to obsolete very soon. Now we are migrating into a new technology which we call PERC cell. Okay, if you're going to work in Jinko, JA, Jinko Solar, JA Solar, Sun Power, what else? Jinko, JA, Q cells, they are all doing PERC cell. Okay, they are doing PERC cell. If you're going to Sun Power, then they're doing PERC, but with a slightly different contact configuration. They're all doing contact at the back. But in this case, it's just a typical technology where you have double-sided contact at the front, at the back. The very same thing from left to right, except if you look at the previous technology, which is called BSF, you have a very thin layer of BSF. BSF here simply means AL doped silicon, AL doped silicon, where you deposit a very thin layer of aluminum, and then you put the wafers into a furnace at high temperature, where the silicon and aluminum will form an alloy. Okay, the alloy is called back surface field, and that the rule is to minimize real surface recombination. So doing this is not so good because you need to have your contact throughout the whole space, throughout the whole real surface. And this is bad because if you learn recombination last time, a metal to silicon interface, is a defective interface. So that means it will induce SRH recombination. So the more areas you have involving metal to silicon interface, the higher the probability of the recombination. Okay, so that's why the new technology is called PERC, passivated emitter. Let me just write it down here and finish it off here. It's almost 11 already. Passivated emitter, real cell. So what it does is the whole thing remains the same except at the back of the cell, where instead of doing the whole space, the whole real surface with the metal, we only contact metal at certain points at the back. So this is the contact point of the metal, the gray one, and you have a heavy doping here and P plus, heavy doping. The green layer is P plus in order to heavily dope under the contact. And then the blue and the yellow here is aluminum oxide and silicon nitride layer, which serves as a passivation layer. Okay, passivation and capping, right? Alox and nitride. Alox and nitride at the rear side. So a big fraction of the rear surface is passivated so that we minimize recombination, and only a specific area of the surface, of the rear surface, is contacted with the metal in order for us to extract the whole, the carriers, through the contact areas. Okay, so the moment you reduce the contact area between metal to silicon interface, we manage to reduce real surface recombination. So that is the essence of this PERC cell technology. And this technology is like 80% of the market now. So daripada 90% of the solar technology that we have based on silicon tu, 80% of the 90% is based on PERC solar cell. And the remaining is heterojunction and blah, blah, right? So I'm just going to stop here about Malaysia as the third largest PV cell. Okay? So done for today. It's almost 11. Any questions for now? So far, okay. Any questions? Okay. Anything on your presentation? Any questions? Coconut a show of something? Anything? All good? All right then. Kalau tak ada soalan, then that's it for today. Bye-bye. Take care. Assalamualaikum.